In this session, we are going to discuss about the rocket equation. How are we going to derive equation for the rocket? Before we derive the equation, we need some basic concept which we can get from Newton's laws, especially second law and third law. First, we discuss about the Newton's second law. What it says: the resultant force is directly proportional to the acceleration, or we can say the product of mass and acceleration. So here the F is known as the resultant force. What is resultant force? Now on an object, more than one force is acting. Let's say here F1 and F2. As the forces are acting in the same direction, the resultant force will be the addition of these two forces. So what will happen here? The resultant force increases. If resultant force increases, the object acceleration also increases. This is one condition. So the acceleration always depend on resultant force. If resultant force is constant, acceleration is also constant. Resultant force increases, acceleration also increases. If resultant force is zero, acceleration also zero. Let's see some example, discuss about some example to know more about the connection between the resultant force and acceleration. Imagine here a skydiver is falling downwards who has the weight of 1000 Newton. So the downward force here is assuming as 1000 Newton. Initially, there is only force of gravity is acting on his body. So there is no external force like air resistance at the beginning, as he right after he jumps out of the aircraft. There is no air resistance acting on his body. There is only gravity, the force of gravity, pulling force. So he is falling at a constant acceleration of 10 meter per second square. The approximately is a round figure. It's actually 9.6, 9.7, 9.8. Here for our easy calculation, for our easy understanding, just we need to know the concept. So I take 10 meter per second square. So that he is falling at the constant acceleration. Let's draw a graph, a velocity time graph here. So a slope line, a straight line. So for some time, for few seconds, he is moving at a constant acceleration. During this time, the velocity of the skydiver increases. After few seconds, what will happen? Air resistance started acting on the body. Initially, the air resistance right after he jumps, the value was 0 Newton. After some second, during with when there is no air resistance, the acceleration is constant. At this particular time, air resistance started acting. So what is happening here? Let's just have some example for air resistance, 100 Newton. Now we are going to find the resultant force. At the beginning, the resultant force was just 1000, because 1000 minus 0. What is here minus? There is no opposite force, so we write here minus. And here the air resistance is, after some time there is an air resistance. The reason of air resistance is because the skydiver is increasing his speed. One of the affecting factor of air resistance is speed. Another affecting factor is the surface area. As the surface area increases, air resistance increases. This is what once he opened the parachute, the acceleration abruptly reduced. Okay, come to this point here. Resultant force, how the resultant force is decreasing here. Now the weight of the body is 1000 negative subtracted by the air resistance. Why it is subtracted here? Because it is opposite in direction. Now the resultant force is reduced. Before it was 1000, now it is 900. So what happened? If you want to find acceleration, force over mass of an object will not be changed. So here 1000 Newton, so the mass is approximately 100. So what happened to the resultant force now? What is the resultant force here? 900. So if we cancel these two values, now the value of acceleration is 9 meter per second square. How much it was before? It was 10 meter per second square. So what happens in the graph? Now it reduces. So when it reduces, it becomes a downward curve. So this part is called acceleration decreases. We cannot say deceleration. Still it is speed is increasing in this time. So we say decreasing acceleration. The acceleration speed increases, but not like the proportion it's not proportionally increasing. So we have the word acceleration decreases, change in acceleration. Why acceleration changes? Resultant force changes. Why resultant force changes? Because air resistance is acting on it. Why air resistance is acting? Because the speed of the skydiver increases. Why speed of skydiver? The speed increases because the gravity pull. Speed increases, air resistance increases, resultant force decreases. I told before, resultant force is directly proportional to the acceleration. As resultant force decreases, acceleration decreases. Until what value it decreases? It decreases to 0. So you can see the graph goes constant parallel to the x-axis. Here we say acceleration is 0. Let's have with example, it will be more interesting. Now what happens? The skydiver, he did not open the parachute. I told before the weight of the skydiver is 1000. Now before, initially at the beginning, the air resistance was 0 Newton. Then it started increasing because I told you the speed affecting factors. The speed increases, air resistance increases. Then it goes higher, 100, 200, 300, 400 means this direction. So until the weight of the skydiver, the air resistance increases. So now if you find the resultant force 1000, this is the weight of the body, minus the air resistance 1000. So now the resultant force is 0. So force is equal to mass into acceleration, acceleration force over mass. Resultant force becomes 0. So 0 divided by mass will be 0 meter per second square. So that's what I told, the resultant force is directly proportional to acceleration. At this point, when the air resistance reaches 1000 equal to the weight, the resultant force 0, so acceleration 0. So this is the main concept. Acceleration decreases. It is because resultant force decreases. If resultant force increases, acceleration also increases. If resultant force is 0, acceleration also 0. Right. Now we can change some factors. Now force is equal to mass times acceleration. So now we can do some small research. Keeping acceleration or the mass constant or the force constant, acceleration constant, we can investigate keeping the factors constant, and then we can investigate the other two factors, how it varies. Okay, now I have a question. A rocket, thrust of the rocket, which means In the rocket, if you see here the top, payload mass on the top, and here there are propellant. The propellant means it is not only the fuel, it is not only fuel, it has the fuel and oxidizer. This fuel, hydrogen fuel, and to burn the hydrogen we need oxygen. So they have both in the fuel tank. So as it is burnt, dm by dt, that is the mass loss of the fuel in every second. In every second, the combustion engine is burning the fuel, and the fuel produces the heat energy. The heat energy expands the gas inside, and it will rush out through the nozzle at the bottom of a rocket, so which gives a downward force onto the ground, and then equal and opposite forces are acting according to Newton's third law. Every action has equal and opposite reaction. So that here the concept is what I'm asking here, the force or the thrust given by the gas, exhaust gas, propellant, is a constant. So if the force, the resultant force is constant, acceleration must be constant. But what happened actually with the rocket? Force is constant here. The thrust, the total force acting on the rocket is constant, but acceleration increases. Is it possible? If the resultant force is constant, acceleration must be constant according to Newton's second law. That's what we have discussed before. But what happens here? In reality, the thrust is equal. The total force given onto the rocket is equal, is constant, but acceleration keep on changing, which means increasing. So how is it possible? So is it wrong? It's a Newton's second law. Will it be wrong? Will it go invalid? No, of course not. If you carefully listen, there are three factors are making the law, Newton's second law. What is that? Force, mass, acceleration. Here the force is constant, so keep this factor constant, force constant, and here the in reality the acceleration increases. In reality acceleration increases. What is the another factor that we have to think about or investigate about? That is the mass. So here what is the mass? Here we have the mass like mass of payload. Payload is nothing but the probe or the things, the stuff which is to be transferred or to be uh, you know taken to the space will be kept on the payload mass on the top of the rocket, and that is the payload mass md plus the propellant mass mp plus the structural mass ms. These are all the total mass of the rocket. Here the propellant mass, which means the fuel, will be containing the total mass. The most of the mass will be from the propellant mass. Will take 91, more than 91 percentage of total mass of the rocket is only from the propellant. So the payload mass and the structural mass, if you add both, if you compare with the propellant mass, will be nothing, will be very small, because it takes up 91 percentage of total rocket mass. So here if you investigate, you will understand constantly the propellant, the fuel, the mass of fuel, the mass of fuel, the propellant mass decreases every 1 second. Every 1 second, the mass of fuel mass decreases. So the total mass of the rocket decreases. So here mass decreases. What happens? Acceleration increases. It is inversely proportional. By keeping the force constant, these two factors are changing. So because of this mass factor, acceleration changes even though the resultant force is constant. So it is not invalid. Newton's second law is not invalid. Even though the force is constant, acceleration is changing. It is because of the fuel mass of the rocket. Here we are going to derive the rocket equation with help of Newton's second law, F is equal to ma. There is another formula is rate of change in momentum. So here dp is change in momentum, and dt is a fraction of time, some given amount of time. Okay, so initially let's take t equal to 0. The velocity here is v, and the velocity of the escaping gas is u, and the mass of the rocket is m. After some time, let's say 1 second, the mass of rocket is reduced because the fuel is being burned. Because of burning fuel, the rocket is getting the thrust and it is accelerating. Now as it is accelerating, its velocity is added up. Some amount of velocity is added up here. So let's have delta v. Some velocity is added. Why some velocity is added? Because acceleration increases. As the mass of fuel decreases, the total mass of the rocket decreases. Even though the thrust is constant, the mass decreases, so acceleration increases, as we discussed before. So force is constant here, mass decreases, so acceleration increases. This is the concept we get from the Newton's second law. So what is the speed of the rocket? It is still the same because the amount of burning mass of fuel is constant. In every second, 1000, let's say an example, 1000 kilogram of oil or the fuel is being burned in every second. This is going to be the same throughout the motion. So here the velocity, the escaping gas velocity is constant and the direction is opposite. Okay, u. Now here we are going to apply it for the conservation of momentum. So conservation of momentum, it says initial momentum is equal to final momentum. So initially the momentum, the total mass of the rocket multiplied by the velocity of the rocket, and final momentum of the rocket. Here there are two momentum is there, the momentum of the rocket and the momentum of the fuel. These two are in the opposite direction. The momentum of the rocket is forward and the momentum of the fuel is backward. So here we know that momentum is mass times velocity. In this final momentum, the mass of the rocket will be m minus dm, as the mass of fuel is burned, so the total mass is reduced, m minus dm. What about the velocity of the rocket? Some velocity is added. So let's have here dv. The velocity is increased. So this one we are going to write here p in the place of p1 m minus dm, the mass of the rocket and the velocity of the rocket. Some amount of velocity is added up here. Plus p2, it is the momentum of the fuel. Momentum of fuel is here reduced. Amount of mass of fuel is being reduced. A constant mass of fuel is being reduced in every second. So what is the velocity? This velocity is v minus u. This reference frame from the earth. This concept is very important. The reference frame, you need to go back and then get the concept, learn the concept of reference frame concept. If we watch the motion of the rocket from the earth, if you see the gas, the escaping gas, the velocity, it's v minus u. The v is the rocket velocity and u is the speed, the escaping gas velocity. It is just opposite from the rocket velocity, so it is in the opposite, so we can assume negative here, but actually it is different concept. That reference frame, you need to know the knowledge of reference frame when we are watching the motion from the earth. So here we can write this value. Instead of p2, I'm going to write here the mass of fuel and the velocity of fuel, v minus u. It is the reference frame from the earth. Here is mv. Now I'm going to simplify this. Mv here minus, we multiply this mv, then multiply this plus mdv and multiply here minus vdm, and this one minus dmdv and multiply this plus vdm and multiply this minus udm. So we can simplify, cancel this, these two are cancelled, then mdv or vdm, positive negative vdm is cancelled, and this mass of fuel, a small amount of mass of fuel and then small amount of velocity is increased. So this is amount is very small, so I'm not going to add this. We can neglect this because the amount comparing the other value, the mass of the rocket, the small amount of fuel can be neglected. So I'm going to write only the two terms here, these two. So mdv is equal to udm. This is the equation we get from this calculation. So I'm continuing from here. Now I have to divide both sides by dt. So dv divided by dt is equal to u dm divided by dt. So dv by dt is called rate of change in velocity is acceleration. So we can write acceleration is equal to u dm by dt. So we know this according to Newton's second law, mass times acceleration is the force is equal to dm by dt. So here the force is the thrust is equal to u dm by dt. So this u is the speed of the fuel, and this is the mass of fuel is being burnt in every second is constant. So this will give the thrust for the rocket. Which one? The speed of fuel and the mass of fuel burned will give the thrust for the rocket. So F is equal to U dm by dt. Now still we are going to derive this formula because the mass of the rocket is not constant. As the fuel is being burnt, we are going to take the integration and going to bring some another formula so that we can apply the limit in the integration, and anytime we can find the speed of rocket. So how are we going to do this? So I'm going to erase this. Now we are going to find the integration. Using integration, we can find the speed of the rocket at any instant of time. So previously we have this formula mdv is equal to udm. Here we take this mass to the denominator and we are going to take the integration dv, and here integration u dm over m. Now we are going to give the limit, the v0 to v1, v0 initial speed to the final speed, whatever the speed, the any at any instant what is the speed we can find from this v1, and here the initial mass to the final mass. So initially m0, final mass m1. So at any instant we can find the velocity of the rocket using this information integration. So dv, the integration if you take, it will be v, and we put the limit here v0 to v1 is equal to, here the u is constant, this dm by m, this is the negative ln. So here the integration, the value will be ln m, and the limit is m0 m1. We are going to apply here. So when you apply this limit, the upper limit minus the lower limit is equal to u. When you apply the limit here, the ln upper limit is m1 divided by the lower limit. Okay. So when you take the limit, means the integration of dm by m is equal to minus ln m minus. So I forgot to put here, so we need this. So minus, then v1 minus v0 is equal to minus u ln m1 m0. This I have written this again. So what are we going to do? I want to change this negative, so here I can take the reciprocal m0 divided by m1. So here v0 initial velocity, v1 final velocity, at the same here m0 m1, here it is initial mass and this is the final mass of the fuel. So we can write this equation, v1 initial speed is 0, so we can cancel it, and here u ln m0 initial mass and divided by final mass m. So using this equation we can find the final speed of rocket at any time. Final speed any given time we can find by substituting m0, that is the initial mass of the rocket, divided by final mass of the rocket. Whatever the value you substitute, and you can find the speed of rocket. or investigate the equation. So v1 minus v0 u ln m1 minus m0. So here is m0 divided by m1, sorry. So what is v1? Final speed, initial speed, speed of the gas exhaust. And here m0, m1, initial mass, and this is the final mass. So now you can initially it is 0, the speed is 0. So we are going to find the speed of the rocket, and the speed of the fuel, let's have like 4000 meter per second, and learn the mass of the initial mass of the rocket 200 or 20 million 10 power 6. Let's have one example, and the final mass is 10 times 10 to the power 6, just half of the mass is reduced. So using this equation we can find the final velocity of the rocket.